Hello, good morning. Our team is formed by Miguel Arellano, Valeria Torres, Diego Davila, and me, Marco Quiroga. We are going to explain the problem number 3. So, the first, the first activity is to consider the following unitary step response and find the transfer function of the approximate second order system, proved and providing the result using a MATLAB simulation. So, we have the plot. So we, by intuition, we got some values. So here, we by intuition we calculate KA, TR, there is the reset time, and TP, there is the peak time. So the TS and the amp, there is overshoot and the settling time. We're going to calculate later. So to calculate omega t, we use a formula that we used in the first section that is in the first order system. So we have this formula to calculate omega t. Well, we clear the formula, but for omega t, there is p over the peak time. There is p over 0.79, and we got this value. So with this, we calculate the beta. There is p minus double omega t plus gr. So we this operation in degrees. So we pass this value to degrees, as the same here. So for beta, we got this value. So for theta, just with this value, we just do this operation to calculate the theta. For theta, we pass to calculate the c. So the c is equals to sine of theta. The sine of theta, we use to calculate the setting time. So the setting time that well we use the formula given by the teacher. So the setting time is 1 minus e to the minus sine of theta. We do this operation and we calculate the setting time. So we pass to calculate the overshoot. That is this formula also given by the teacher. That is the same as the first order system. So after we calculate the overshoot, we pass to calculate the omega n. So omega n is equals to omega t divided by sine of beta. So this equals we just already have these two values. So omega t divided by sine of beta is this value. After this, we calculate the sigma. So sigma is equal to c plus omega n. So after we do this operation, we got this value. After we got all the values for this system, we just pass to formulate the transfer function. So we got this transfer function as the general transfer function. We just are going to put the values in each side of the general formula. So we put the k in this case. K is just not 1 because a is just 1, and for k in this side we're going to put 0.059. So here we put the k in omega n we put this value. In this side we are going to multiply 2 by c by omega n, and this side we are going to just multiply omega n by itself again. So we got this transfer function, and we're going to pass to MATLAB to simulate and upload this transfer function to compare it by the given by the teacher.
We go we pass to the MATLAB simulation. So for the first step, we need to declare the variables given this as the transfer function of the problem. So we declare a as 1 because of the s relate to the 2. We declare b to the coefficients of the s, and we declare to declare c as the last coefficient of the transfer function. Also, we declare x as k plus omega n, and we plot this coefficient. And the result is the same transfer function that we have just here. The plot, you can see the plot is similar to the one by the teacher given.
For the problem number 2, we have to design the transfer function of a second order system that it has the following characteristics, and we must to prove the result with a MATLAB simulation. Characteristics is a unitary state gain, 10% of overshoot, and 1 second of rise time. We go to the procedure, and we have the same values that I just say here. K equals to 1, and P equals to 10% or 0.1, and TR is equal to 1 second. We know that TR is equal to P minus beta divided by omega t. This formula is given by the teacher. That is the overshoot, and P equals to all of this. We clip the sigma, and we got the sigma is equals to 0.5912. Then we calculate the theta with the sigma. So the theta is equals to 36.242. With the theta, we calculate the beta. The beta is equal to the 90 minus the theta. So after we calculate the beta, we just pass this value of beta to radians. So after we calculate the beta in radians, we're going to clear in this formula to omega t. We got the value of omega t, this one, and with omega t we calculate omega n. So after we calculate omega n, we just can pass it to the transfer function, and this is all the transfer function that we got for the system.
So for the MATLAB simulation for the problem number 2, we have omega n as 2.5380 and a C as 0.5912. We do a square to omega n and we see the value right here. So we now can plot the transfer function for this. So at body of the transfer function we have a k equals to 1. So we can just put the omega n squared, and below of the transfer function we have a coefficient of 1 in the s square, a coefficient right here, a 2 plus s c and plus omega n, and the third coefficient we put omega n as the omega n square and plot this. You can see this transfer function as the same as the last problem, and we see the plot right here. You can see if we calculate the TP, you can see the values of the TP right here. So all this TP is going to be right here, 1.4 something. So you can assume the problem is just right.
For the problem number 3, we have to consider a system with the following state space model using the synthetic division to find dominant poles and the approximate following parameters. Also, we need to have to perform a MATLAB simulation to test the result gotten. We need to calculate the overshoot, the MP, and the peak time. So we have this state space model, and we pass to the procedure. We this state space model. First of all, we need to subtract this matrix A for the matrix identity plus the S. So this matrix identity we subtract to the matrix A, and this is the result. We need to calculate the determinant of this matrix. So after doing the determinant of the matrix, we know that the equation gotten is this one. So after the equation, we use the division to calculate the dominant poles. So we know that a factor of the synthetic division is -10 because we got a 0 in the last section. So as we see in this graph, the dominant poles is this one because S plus 10 is so far behind the origin and is going to disappear in some time. So the dominant poles will be this one. After this, we calculate the dominant poles, and we continue to calculate the variables of the transfer function of this system. So we know that omega n is equals to 17.
For the MATLAB simulation, we're going to consider a key equals to 1 as unity steady state gain. So if we consider declare the omega n. It's going to be W plus root of 17. After this, we calculate the sigma. It's going to be S is equals to 1 divided of the root of 17 that we just calculate. So we're going to put W. After this, we're going to put it in the transfer function, the general transfer function. So of the transfer function, we have a k that is equals to 1, and well, before this, we're going to put in our variable omega is going to be equals x omega n to the 2 is equal to 17. So put the general transfer function up is key plus omega n is going to be x. The first coefficient of below the transfer function is going to be 1. The right here is going to be 2 plus 2 plus sigma. If you guys see that sigma and W is just the inverse, so it's like it's just like if you guys put 1, because the multiply of W and S is going to be equals to 1, so we're going to put just 2, and the third coefficient we're going to put x, because here is the omega n to the 2, and with voltage we see the plot, and you guys can see the key key A is just 1 right here, and as we have a TP peak time equals more or less like, oh, let's see, TP is equals to 0.7853. The plot, you guys can see that right here the peak time is equals approximate to 0.78 right here, so you can assume that it's just right, this plot.
For the problem number 4, we have to consider a system with the following transfer function. Given this transfer function, we have to find the value of kind necessary for the system to have an overshoot of 25%. Also, we need to prove the result with a MATLAB simulation. Well, we go to the problem. So we know that the MP, the overshoot, is equals to 25%. That means is 0.25. Then we must apply to the formula given by the teacher there is this to calculate sigma. So uh, we clear sigma in this for this formula, and with the value of MP, the overshoot, we got this value for sigma that is 0.4035 37. Sorry. After we got sigma, we calculate the omega n using this formula. There, omega n is equals to 5 between 5 divided by sigma. That the value for omega n is equals to 12.38. After we got omega n, we calculate the k. So k is equal to omega n elevated to the 2. We elevate this value to the 2, and for the k, we must apply. We got a value of 153.39. So the answer of this problem is this one.
Well, we pass to the MATLAB simulation. So the first step is to calculate the coefficients. We declare them like as first of all k is going to be equals to the one we calculated before. Then we declare omega n is going to equals to w. Then we declare the coefficient below the division. The first coefficient will be a3. It's going to be equals to 1. b3 is going to be equals 2 plus sigma. Sigma is 0.437 plus omega n the third coefficient is C3 is omega n to the 2. So for the transfer function, we put the values we just declared. That is k plus omega n to the 2. We put the omega n that is equals to C3. Omega n elevate to the 2. We put here the A3, the B3, and C3, and we got this plot of the problem with a k of 153, omega n 12.38, and a sigma of 0.4037. Thank you.